So one tool that we can use to analyze interdependence is game theory. And game theory just kind of says, if one player does this, how will the other one respond, and so on and so forth, and tries to use that to come up with what is the most likely outcome. It's often done through a grid, at least. I mean, obviously, once you get far enough on, it's all done via hard maths, but we can just visualize it using a grid, in which we're going to put one player down here, player A, and let's imagine we're looking at pricing decisions. It doesn't have to be this, it can be anything, but let's imagine that A has the choice of high price or low price. So A's decisions we're playing up and down. B over here, they also have a choice of high price or low price. And that gives us 4 quadrants. Here, they're both high. Here, they're both low. In this one, B remains high, but A is low. So that's low, high, low, low, high, high. And over here, we're saying that A has remained high, and B is low. And I'm putting B second, So B is low in both of those, and B is high in both of those. A is high in both of those, and low in the bottom ones. So we have the 4 different possible combinations of pricing strategies are outlined by those 4 boxes. So up here they're both high, and let's suppose that this is, say, profits or revenue in millions of pounds. A does, we'll assume that both firms are doing quite well. There's no reason the numbers should be the same. There's no reason the businesses should be identical. So what's happening in this box then? Here, A is low and B is high. A is undercutting, so presumably, therefore, is going to do better. Whereas B is going to end up doing much worse. So B's numbers are going to put in blue. Up here, it's kind of the mirror image. A has remained high, but B is low. So A, presumably, bad things are going to happen to them. And good things are going to happen to B. Down in the bottom corner, they're both low. This is a price war. Bad things happening. Each firm is losing. Let's suppose that's, say, 35. And 30 for the sake of whatever, 40 for the sake of argument. Okay. So that hasn't helped us necessarily very much. What we're going to be able to do is to analyze this matrix to kind of say, well, what do we think is going to happen? And as part of this, we'll come across some terminology, but I'll introduce that as we go. Let's just look at how we would set about analyzing a matrix like this. And the way we do it is we just take, we assume that one of the players does something, and then say, what will the other one do? So let's start by saying, let's imagine that A decides that what they're going to do is they're going to play high. So what we do is we'd say, well, if A plays high, what would B do? And we look at B's numbers. So we're saying A is high, so we're reading across here. What are B's opportunities? B could play high and get 90, or they could play low and get 140. What I'm going to do is say, well, obviously 140 is better than 90, so I'm going to double underline that, to show that is the preferred option if A plays high. B would play low. We now move on to another one and say, well, okay, what if A plays low? Let's look at the other one of A. So now we've done this one as well. If A plays low, again, we say, how will B respond to that? B has a choice. They could play high and get 20, or they could play low and get 40. 40 is better than 20, so we can put a double underlining there. We now reverse it and say, well, okay, let's now say, let's look at A's responses to what B does. Now we're going to go up here and say, let's suppose that B plays high. What's A going to do? A's numbers, A can either go high or low. A's numbers are either 100 or 150. 150 is more than 100, so therefore A would go low in that case. And lastly, what if B was to go low? What would A do? Again, A has a choice of playing high and getting 25, or playing low and getting 35, in which case they do that. So what we said, and what you'll find is that if you find a double underlining after this process in one box, that's the equilibrium, and it's called a Nash equilibrium. Which I'll define in a minute. But what we're saying is that, given the logical outcomes, if B plays high, A plays low, if B plays low, A plays low, and so on, it takes us to there. That is the Nash equilibrium. And a Nash equilibrium is simply defined as a set of strategies such that no player can gain by being the first to change. So no one wants to change if we're in a Nash equilibrium. Or I sometimes put it, or a student once said this to me, you move, you lose. So let's look at each one of those four quadrants and see whether nobody can gain by benefiting. Let's take the top left. Is that a Nash equilibrium? The answer is no, because by going low, A could get 150, or by going low, B could get 140. Fine, so that's not a Nash equilibrium. What about this one? Is this a Nash equilibrium? A's doing great, but B would realise that if they went from high to low, they would gain. So that's not a Nash equilibrium. This one, B's doing great, but A's doing badly. A realises that if they were to go low, then they would benefit. So that's not a Nash equilibrium. So finally, let's look at this one. Is this a Nash equilibrium? The answer is yes. So it's a Nash equilibrium because there are two underlinings in this box. But it's also a Nash equilibrium because if we look at what happens when each player changes. If A changes, from low to high, they would lose. They would get -10 by doing that. They go from 35 to 25. And therefore, they don't want to do that. What about B? B has 40 in the bottom left by playing low. If they played high, then they would go from 40 to 20. They would lose 20, so they don't want to do that. Therefore, that bottom right-hand box is what's called a Nash equilibrium. A situation in which no player can gain by changing their strategy unilaterally. So even if initially both players were cooperating in some way and playing high, there is a big incentive for them to go low. Another relevant concept, I'll talk in another video about how this applies to oligopoly. I'm just talking about how to solve a game theory grid and outlining the terminology. Another important piece of terminology is what's called a dominant strategy. A dominant strategy is one that a player will select regardless of what the other player does. So dominant strategy, it doesn't matter what the other player does, you're going to do this. And in fact, in this case, there are two dominant strategies, and you'll see why. If player B plays high, we've said that what player A is going to do is they're going to play low. If player B plays low, again, player A plays low. So player A has a dominant strategy of low, but it's also true the other way around. If you look at when player A plays high, player B will play low. Likewise down here, if A plays low, player B plays low. So in this case, both players have what's called a dominant strategy of playing low. However, you don't need both players to have a dominant strategy to reach a Nash equilibrium. And that's what we'll explore in a minute. So let's now look at some, let's now mess about with this idea of dominant strategies. So that's the key to solving a game theory grid. But let's now mess around with some scenarios. So let's imagine we have, again, we're going to go A and B, high price, low price, high price, low price. What I'm going to do is I'm going to give A a dominant strategy of playing playing low. So let's suppose B plays high, A gets 70, but if A goes low, they get 100. Over here, let's imagine that's 30 and 60. So whatever happens with B, those are A's numbers. Whatever happens, A's going to play low. But B, I'm going to give a not dominant strategy. I'm going to say if A plays high, it's best for B to play high. but if A plays low, it's best for B to play low. There's some random numbers. Let's solve this box. What we'll now find is, okay, if B plays high, 100 is greater than 70. Yeah, so A will play low. If B plays low, 60 is greater than 30. So, again, A is going to play low. If we now look at B, if A plays high, B is going to play high, because 80 is more than 40. And finally, if A plays low, yeah, B is going to play low. Yeah, so 70 is greater than that. So again, we still end up with a Nash equilibrium there. But I could have changed the numbers so we could have a Nash equilibrium in a different place. Imagine, I could have created a situation where actually B has a dominant strategy playing high, then we'd end up there. Yeah, the only thing I changed was those two numbers. Yeah, that should be blue, but 90 is more than 70. The Nash equilibrium is in the bottom left-hand corner. So it doesn't. But what I was saying was that in the original one that I created, only A had the dominant strategy, but we still found a Nash equilibrium. It's also possible for there to be no Nash equilibrium. Yeah. So if I construct a situation like that where if B plays high, A plays low, if A plays low, then B stays high. Then if A is low, then B's low. So we'll go 110 there, and 60 here. If B's low, we'll make A go high. So we'll call that 100. And we'll make this one. That should be black, sorry. 100. And if we make that one 60, then what you'll see is there is no Nash equilibrium here unless I've messed this up. So let's suppose we're here. If we're both high, we can see that A has an incentive to play low. So therefore, we'd move to this box. But in this box, where A's got 100 and B has 90, B can gain by going to there and getting 110. So that's not stable, that's not stable. Likewise down here, if we were both at low, A can gain by going up there to 100. So that's not a Nash equilibrium. But then finally, nor is this, because B would now switch to go high because 80 is greater than 60. So that's not a Nash equilibrium either. Or if we do it through the underlining, system, if B plays high, A plays low. If B plays low, 100 is more than 60. A plays high. If A plays high, B plays high, and finally, if A plays low, B plays low. The underlinings are all in different boxes. Therefore there is no Nash equilibrium. And lastly, it's possible to have more than one Nash equilibrium. Imagine you have two firms where really they're linked to one another. Like I don't know, a bowling alley and kind of restaurant or something, and they're hoping that each one will benefit from the other. Then what we might say, so here's player A, here's player B. We could be in town or out of town when we decide where to locate. B could be in town or out of town when they decide where to locate. And if they're both in town, then they're both going to get a high reward because the bowling alley customers will go to the restaurant. The restaurant, so let's call B the restaurant and A is the bowling alley for the sake of argument. If they're both out of town, likewise, it's good for the bowling alley, and it's also good for the restaurant. If the restaurant is in town but the bowling alley's out of town, then it's less good for either of them, because they don't get any of that crossover trade. And the bowling alley loses the restaurant customers who might have gone bowling, and the other way around. So we end up with kind of lower numbers. And likewise, if the bowling alley's in town and the restaurant's out of town, again, that's not going to be great, or it's going to be less good for either of them. So if we analyse this grid, last of all, then if the bowling alley is in town, if the restaurant is in town, where does the bowling alley want to be? the bowling alley's numbers are 150, so the bowling alley will want to be in town. If the restaurant is out of town, where does the bowling alley want to be? 110 is greater than 70, so they're going to want to be out of town. Let's suppose that the bowling alley is in town. Where does the restaurant want to be? 90 is greater than 30, so they want to be in town. And likewise, if the bowling alley is out of town, guess what? The restaurant wants to be out of town. So what you've got two Nash equilibrium. Two Nash equilibria. Neither player would want to change in this case. If they're both out of town, then if suddenly A goes in town, they lose. If B goes into town, they lose. So that would be a Nash equilibrium. But likewise, up here, if they're both in town, A certainly doesn't want to go out of town because they lose, and likewise, B doesn't want to go out of town because they lose. So that's the ideas. Those are the key kind of ideas behind game theory grids. To find a Nash equilibrium, which is a situation where neither player wants to unilaterally deviate, neither player wants to be the first to move, all you do is you take each player's strategy in turn and say, what will the other player do? Underline the higher number, assuming that high numbers are good. If you find two underlinings in one box, that's the Nash equilibrium. You can then explain why it's the Nash equilibrium by showing how each player would lose if they change from it. Other relevant concept is a dominant strategy, which is where I do this regardless of what the other player does. In this case, neither player has a dominant strategy because it's all highly dependent. And just to be clear, it's not, there can be any number of Nash, well, not any number, but we've shown situations where there can be 0, 1, or 2 Nash equilibria in the market. And the Nash equilibria isn't the highest combination of numbers. The very first example that we showed, the best combination for the two firms would have been high, but that's not where the Nash equilibrium was. And what we're going to do in the next few videos is show how we can use game theory to analyze firms' pricing strategies.